Welcome back to our course on blockchain. So, we are discussing about the consensus model in the permissionless blockchain. So, in the last class we have seen that this permission models or proof of work consensus mechanism, it uses this challenge response strategy to decide that one miner would eventually be the leader, and the miner is going to propose a new block that is going to get added to the blockchain. So, the miners they generate a proof, and that particular proof is appended or included in the block which others can verify, and then add that block to their local copy of the blockchain. Now, with this what we do that we are going to cover today is first this proof of work mechanism, and if you remember in the last class we stopped at the point where we tried to see that if there are more than one miners who are going to propose a new block, then what happens, and in this context we are going to discuss about a terminology called fork. We are going to look into what fork is and how fork impact the structure of a proof of work blockchain, and then we are going to see about the different attacks which are possible on proof of work, and one interesting problem of this proof of work idea, that is called the monopoly problem. So, these are the keywords: fork, security, and 51% attack that we are going to discuss today. So, to start with, this is where we stopped in the last lecture, that individual miners they are trying to find out a proof which is going to get appended with the block. So, they have been given a challenge in the form of finding out the nonce corresponds to a cryptographic hash function, and the miner who is able to solve the puzzle becomes the leader. Well, and the block from the leader is appended in the blockchain. So, that was the kind of our broad idea. Now, the question that comes here is that what if two miners solve the puzzle simultaneously, and this can always happen, right, because ultimately it is a kind of brute force method. Everyone is trying to find out a solution. So, it might always happen that two miners they are able to find out the solution almost at the same instance of time. Well, there is no much difference between the time instances when they are being able to find out the solution. So, ideally what should happen, that whenever a miner finds out a solution, the miner uses the gossip to broadcast that solution to the entire blockchain network, and eventually the other miners receive that solution and they stop the mining procedure and starts with the next block. But it might always happen that say here miner 3. So, when miner 3 is has found out this solution and miner 3 is say gossiping this block to others, at that time miner 1 has not heard of the block which have been broadcast from miner 3, and what miner 1 does, that miner 1 also finds out the solution at that instance of time, and miner 1 also broadcast that information through that gossip protocol. Well, so that way from two part of the network two different blocks gets propagated. Well, so this kind of scenario may happen say when there are two miners who are kind of far apart in the network. Well, so just assume that they are far apart in the network, and say this is say one miner and this is another miner, they are far apart. So, by the time this miner has propagated say block B2, this miner has not heard of it, and this miner starts propagated block say B3. Well, so two of the blocks gets propagated simultaneously in the network. Now, the question comes that when two of the miners are propagating the block simultaneously, how we can resolve this conflict, and what I am going to ensure in response to this particular problem. Now, the observation that we have is that both of these blocks that are getting proposed, both of these blocks are the correct blocks, well, or they are the kind of valid blocks. Now, that means from the safety 1 perspective that we mentioned earlier, both of the blocks satisfy that. Well, now what I need to ensure? I need to ensure that eventually safety 2 is getting guaranteed. So, I cannot completely do away with safety 2, that means the consensus finality. So, what I need to ensure that, well, it might happen that momentarily both the blocks get added to the blockchain or both the blocks gets propagated in the blockchain, but eventually one of the blocks get used. Well, so that we typically call as the eventual consensus. Well, so I want to support this eventual consensus in terms of consensus finality. Well, so this is something that I want to support in this case. So, the question comes that how we can support this eventual consensus finality in such a scenario when multiple blocks are getting propagated. So, the idea that is being used in proof of work mechanism is something like that, that momentarily you add both the blocks in the blockchain. Well, now whenever you have both the blocks in the blockchain, so here you see that ultimately your blockchain takes structure of a tree, and in that case one of the branch that I need to prune eventually. Well, so either I need to accept this branch or I need to accept this branch. Well, so for example, if I accept this branch, then the other branch we call it as a fork. So, fork basically means that the branch which I am eventually pruning from my blockchain. So, eventually I am saying that this is not the part of the main chain and this is a fork. Okay. So, these are the two terms we are going to use. So, one is called main chain and the second one is fork. Well, so that way whenever you have say two different part of the blockchain, in that case say I have one block followed by another block, and from this block I have two different entries. Well, and say eventually people are adding multiple blocks here. So, eventually we see that, well, one particular chain becomes the part of the longest chain. So, this part becomes my part of the main chain. Okay. So, this becomes my main chain, and the other part which is not been used any further. So, that means this part. So, that we call as the fork. So, what is my requirement? My requirement is that eventually I need to designate one of this branch as the fork. So, the question comes that how can I find out that which branch is going to be forked? Well, so this is the thing that we are going to discuss, that how I can ensure that one of these branches become part of the main chain and another branch becomes a fork. Well, so to meet this requirement, what we see that, as I mentioned earlier, that momentarily the consensus finality is not ensured. So, that means for the time being, although I meet the requirements for safety 1, I am not been able to meet the requirements for safety 2. Well, and within that instance of time my network remains partitioned. Well, so why I say that the network remains partitioned? Because part of the network sees one block and part of the network sees a different block. Well, so the question comes that how I am going to resolve this particular case, particular conflicting case in case of proof of work consensus. So, what the miners does, that momentarily the miners remove the transactions corresponding to both the blocks from their unconfirmed transaction list. So, earlier what we have seen that whenever a block gets committed in the blockchain and the miners are able to see that updated block, they remove the transactions corresponds to that block from their unconfirmed transaction list. But here in this case the miner sees that there are two blocks which have got added in the blockchain. Now, whenever the miners observe that there are two blocks which got added in the blockchain, what the miners does that momentarily they removed the list of transactions which are part of both the blocks. Well, but remember that is a momentary decision, and then they starts mining the next block. Well, now these forks they are resolved eventually. Now, for the next block creation, what a miner does for the next block, the miners has two options. Either the miner has to accept this block as the next block, or it has to accept the other block as the next block. So, the question comes that whether the miner is going to accept this block as the next block or this second block as the next block. Okay? That we want to find out. Now, what the miner does, that miner accepts the previous block that it hears from majority of the neighbor, okay, or majority of the peers. So, that basically means say whenever you have such multiple different blocks that you are hearing, say assume this is a node which is hearing from multiple different other peers. So, it is actually hearing the blocks from its peers. Now, among 4 of these neighbors, it has heard, so I am just naming this block as say B and B prime. So, it has heard B from 3 of its peer and B prime from 1 of its peers. Now, if that is the case, then this particular miner which is at the center, it will accept the block which it has heard from majority of the peers. Now, here it has heard this block from block B from majority of these peers. So, it will accept block B as the next block. Well, now you might ask the question that what if it hears the block from same number of peers, say for example, 2 of the peers says B and 2 others says B prime, that can also happen. Now, if that is the case, then what the miner does, miners just randomly select one of the block. Okay? And although I am using the term miner, but that this particular rule is actually followed by all the nodes of a blockchain. So, every node in the blockchain, whatever information it gets from its peers, whatever it gets from majority of its peers, it accepts that information. Well, whenever there is a kind of conflict of information like this, that everyone says that well after block B 0, someone says that the next block is B, someone says that the next block is B prime. Okay. So, the question comes that which one you are going to accept. Now, to resolve this question, every node in the blockchain applies this rule which we call as the majority rule. So, what the majority rule says, that the majority rule says that you accept the information which you are receiving from majority of your peers. Well, now in the case whenever you are receiving the information from same number of peers, then you randomly select one. Well, so to break the tie. So, this is the kind of core idea about selecting the next block or selecting the previous block for a newly mined block. Now, with this what will happen that eventually one of the chain will be used by majority of the participants in the blockchain. Well, so for example, the next miner, the miner which is been able to select the or mine the next block, that particular miner what it does, that miner say select this block as the next block. Okay. So, this block as the next block. Now, whenever the miner is selecting this block as the next block, then the other block that is becoming the fork, because this particular chain becomes the part of the main chain. Well, so that is the kind of idea which is applied here for this kind of conflict resolution, and with this eventual resolution of this consensus information, eventually one block becomes part of the main chain, right, and the other blocks become a fork. Well, so here this particular block becomes the fork. Well, now whenever I have this, now whenever a particular block has been marked as the fork block, then the miners, they basically look into the transactions which are there in the fork block, okay, and they try to see whether those transactions have already been committed or not. So, if I just try to look into the transactions in this fork block, I can see that transaction 16 is committed here, transaction 17 is committed here, transaction 87 is not here and at the same time not in this block. So, transaction 87 has not been committed. Similarly, transaction 49, it is not there in this block, also not there in this block. So, transaction 49 has also not been committed. So, that way it identifies the transactions which are not there in a which are not there in a particular block. Now, whenever a transaction is not there in a particular block, so what the miner does, that the miners means reinitiate this or put these transactions within the unconfirmed transaction list. So, here transaction 87 and transaction 49, that will be put in the unconfirmed transaction list of the miners and they will try to propose a new block with these transactions included. Well, so that way if a transaction is not the part of a fork block, then if a transaction is a part of the fork block and not been committed as a part of the main chain, then those transactions are taken up under the unconfirmed transaction list and they are eventually being incorporated in a future block of the blockchain. Now, the question comes that what we see here, that we cannot immediately say that a block has been forked or not. So, it might also happen that another miner, it has not heard these two blocks and it uses this green block as the previous block and starts mining the new block. So, that can always happen because we are in an asynchronous network. It might happen that a miner is at a slow network and so on. Now, for these particular cases, what typically the proof of work blockchain does, that it poses certain constraints on the blockchain system. So, for example, what Bitcoin does, that it makes a restriction that you cannot use a transactions until you get a confirmation of 6 blocks. Well, so what is mean by confirmation of 6 blocks? Say your transaction say has been committed in this block. If your transaction is in this block, then after this block there should be 6 other blocks to ensure that your transaction is finally committed. Well, so that we call as the eventual consensus finality. So, that means if you remember that the safety 2 property we are not been able to support immediately, but what we are ensuring that eventually I will check for that many number of blocks. If the block does not become a fork within that many number of further block addition, then we consider that block as a confirmed block and the transaction as a confirmed transaction. So, eventually that safety is being ensured, although safety is not ensured immediately. So, this is the kind of way proof of work mechanism ensures consensus in an open environment. Now, as I mentioned earlier that for all such kind of consensus mechanisms, there are certain type of attacks which can be possible. So, here in this context, let us try to see that what are the different types of attacks which are possible on proof of work blockchain. So, if you try to see that what are the type of attacks that are possible and the security measures that are being taken on proof of work blockchain, one of the prominent attack is the Sybil attack. So, what is a Sybil attack? The Sybil attack basically means that the attacker attempts to fill the network with the clients under its control. Well, so that means I am an attacker, I can create multiple of my identity and I can actually fill up the network with those identities. So, for example, I can create one node with one IP address, another node with another IP address, or even under the same IP address I can use 2 different public address to have 2 different wallet to participate. Well, so that way I can create multiple different public addresses, because you remember in the context of Bitcoin you have learned that this identity is basically generated from this public key. So, that way I can have or I can generate multiple of the public keys and use that public keys to post multiple of my identities, whereas I am an attacker. So, that way an attacker can post the attacks that we call as the Sybil attack. to take control of the network by representing multiple of its identities. Say that can create different kind of attacks, like it can those false identities can refuse to relay valid blocks, or they can relay attack blocks. Well, so the solution that is being applied, so again different blockchain apply different kind of solution. This is typically the solution that is applied in Bitcoin blockchain. So the idea that Bitcoin blockchain uses, that it diversifies the connection. That means Bitcoin allows one outbound connection to per /16 block of IP addresses. Well, so for example, you cannot make both 202.141.81.2/16 and 202.141.80.18/16 as your peer. Well, so the way you are creating the peers, you need to ensure that you are exactly using one IP address out of all the /16 subnets as your peer. Well, so you should not use more than one IP address on that from that subnet as your peer. So the basic idea is that whenever an attacker creates multiple such identities, it is most likely that all the identities are within the same subnet, well, or majority of the identities are within the same subnet where the attacker actually belongs. The second attack is the denial of service attack. The denial of service attack is basically one particular attacker, it sends a lot of data to a node, say lot of transactions. So it blocked the processing power of the node. So that way, say you are just going to validate the transactions, and those are kind of say invalid transactions, and you are omitting them from the blockchain. And the solution for this problem is that you limit the forwarding of blocks. Well, so for example, you disconnect a peer that is sending too many transactions. So these are the kind of most ad hoc solution that are adopted by Bitcoin to solve such kind of problems which can happen in a proof of work blockchain, or rather these are the kind of common attacks which can happen on a distributed system. Now, if you just ask me the question that this proof of work, as we mentioned earlier, it relies on this 50% hashing power. So what we assume that the attackers cannot get the majority of the hash power, and that way I have a kind of truly decentralized network where I am running my blockchain application. Now, Bitcoin proof of work, it is computationally difficult to break because the attacker need to gain control of 50% of the hash power, at least 50% or even more than 50% of the hash power, but theoretically it is not impossible. Well, because if your network is not that large, it is easy to control more than 50% of the participants. So, for example, if you create a blockchain network, if you create an open blockchain network only with 10 nodes, well, then an attacker can always take control of 6 of those nodes. Well, and the moment attacker is taking control of 6 of those nodes, the system is compromised. And on the other hand, the attacker can deploy high power server to do more work than the total work of the blockchain. Okay. So, my basic principle is that if you say if I have a blockchain, well, which are connected to this hashing power, say I have a block followed by another block, followed by the third block, fourth block, and so on. Now, if you want to make an attack on this particular block, what you have to actually do, you need to change the hash value of this block. Okay. Now, whenever you are going to change the hash value of this block, so ideally this the next block, it contains the hash of the previous block. So, that way if you want to make change the hash of this one, then you need to make a change here. Well, you also this, if you want to make changes here, you need to make changes here, and so on. Well, now that way you need to, and changing the hash basically means you need to find out a new nonce, and finding out a new nonce, as we have seen earlier, it is a computationally difficult task. Now, because it is a computationally difficult task, so that way by the time you are actually making changes in these consecutive blocks, new blocks are getting added to the blockchain. Well, so that way the idea is that an attacker will never be able to compromise all the future blocks which are getting added to the blockchain. Well, but what if the attacker has more hash power compared to the hash power of all these blocks in the blockchain. So, for example, the attacker is want to compromise this particular node, and whenever the attacker is trying to compromise this particular node, during that time what the attacker has to do, attacker actually has to compromise the other nodes which have been added there. Now, say if I just assume that the total hash power of these nodes is equal to PB and the hash power for the attacker is equal to PA and PA is greater than PB, then the attacker will be able to make the attack, because attacker is basically generating the hash in a much faster way compared to the rate at which the blocks are getting added. Well, so if that is the case, then the attackers will be able to do the attack, means which is theoretically possible, but practically the computation devices that we have with us and the computation power that we have with us, raising such kind of attack is a bit difficult. But as I mentioned that the attack, it is difficult to raise the attack, but it is not completely impossible to raise the attack. Well, so there are multiple known cases of successful double spending on Bitcoin. Say for example, in November 2013, ghash.io, that mining pool appeared to be engaging in a repeated payment fraud against Bitcoin Dice, which is a gambling site. They were able to successfully did that kind of double spending. Well, and it was possible to break the proof of work mechanism. I mean, theoretically possible, and people did that earlier. So, in that context, this monopoly problem comes. So, the monopoly problem says that proof of work depends on the computation resources available to the miners. So, the miners having more resources have more probability to complete the work. Well, and that actually raises the kind of monopoly problem which is there. So, what might happen that a miner is there in a position, the miner does not have sufficient amount of computing power, or the miner is there in a slow network, then it is very difficult for those miners to propose a new block. Well, and such kind of monopoly can increase over time. So, it is actually a kind of very interesting game theoretic construct which is known as the tragedy of commons. So, if you are interested to look into the mathematical aspect of this postulate, that why such kind of monopoly should increase over time, you should look into this game theoretic problem of tragedy of the commons. So, it is a kind of nice statistical construct with a game theory base to show that in such kind of architecture the monopoly increases over time. Well, so if I just try to theoretically or conceptually explain it, it is something like that the miners will get less reward over time, because this mining reward comes from the amount that is being returned by the successful block inclusion from the Bitcoin network. Now, as we have seen earlier that over the time that reward gets decreased. So, that way the miners will get less reward over time, and as the miners will get less reward over time, the users will get discouraged to join as the miner. Well, and when the users will get discouraged to join as the miner, few miners with large computing power may get control over the network. So, that can be a kind of possible problem in case of a proof of work blockchain. Well, and in case of there is a monopoly problem, there can be this 51% attack which says that a group of miners can control more than 50% of the hash rate of the network. Well, so if that happens, then your entire security of proof of work mechanism that gets destroyed. Well, the moment these dishonest people becomes majority in your entire network. For the time being, it is hypothetical, but it is not impossible. For the time being, the Bitcoin network is very large. So, it is difficult to have such kind of monopoly problem on the Bitcoin network, but such kind of monopoly, that 51% attack, it happened for other network, other blockchain network like that Krypton blockchain network. Krypton is one Ethereum based blockchain architecture. On top of that Krypton, there was an 51% attack around August 2016, and the idea was that at that time the network was not that large, and when the network is not that large, it is easier for the attacker to collude the participants in the network. Well, and the moment the attacker is get control over more than 50% of the participate in terms of gaining more than 50% of the hash rate of the network, the attacker can actually collude the network. Well, so that is known as the 51% attack. Now, in conclusion, what we have seen today, that proof of work may result a fork. So, that way consensus finality is not ensured when a block is getting added. Eventually, we try to ensure the consensus finality by putting up certain constraint that, well, a block once added will not be the transactions will not be usable until 6 other block commits. And the security of the proof of work is ensured with the condition that the attackers cannot gain more than 50% of the hash power. Well, so that is the kind of limitations of a proof of work blockchain that you should always keep in your mind while designing any application with the help of proof of work blockchain. So, you need to ensure that your network is sufficiently large, so that the attacker does not get control of more than 50% of the hash power of your network. Well, so with this let me conclude today's lecture. So, in the next class we are going to see certain other limitations of this proof of work blockchain, and we will see that the different variants of proof of work that have been discussed or that have been designed over time to solve the inherent problems within the proof of work based consensus mechanism. So, thank you all for attending today's class. See you all in the next lecture.